Welcome. In this session, we'll learn how much energy is stored in the inductor. Now, in the previous session, we learned when we connect an RL network to a source through a switch, all right? So we connected it like this. So this is R, this is L, and we saw a current will flow. And the behavior of the inductor current looks like this. It is Vs by R1 minus e to the power of t by tau. And how much is tau? Tau is simply L by R. That's referred as the time constant of this circuit. All right. Now, let's assume that the inductor voltage is charged. Sorry, inductor is charged to some current value. At any instant of time t, the inductor is charged to some value. Yes. So at any instant equal to t, the inductor current has risen to this value. Means inductor now stores this much of current. All right. Now, based on this storage of the current, how much energy will be stored in the inductor? All right. Let's derive that. Now we know the power, instantaneous power in the inductor is given by the voltage across the inductor and current through this inductor. Now we can write it like this. We can write it as I times V. V is given as di by dt. So simply we can write it as, okay, let me use the common I here, I by dt. So that means it will be L I by di by dt. So this is the power, instantaneous power. Now, if we have turned on the switch at t equal to 0 and kept it there for some time, some time equal to t. So we have kept the switch in closed position for time equal to t. Now, how much energy will be stored in this? Now, for that we can calculate using the relationship of energy and power. So how much, this is the instantaneous power that's flowing there. So the energy that's acquired by this inductor in this time from 0 to t, because we have turned on the switch at t equal to 0, and we have kept it for t seconds or t minutes or t hours, whatever is the unit of t. So this will be simply p times dt. So how much is the value of p? Substituted from this, so we'll get p L I di by dt. Now, as you can see, dt and dt will cancel. So we are left with 0 to t L I di. Now, so this integration is now with respect to I, right? So you can see the integration is now changed with respect to I, and you can see L is a constant. So we can write it like this, 0 to t I di. And I said suppose the value of the current that this inductor stores in time t is I naught. So we can say, we can change the limits at t equal to 0, the value of the inductor current is 0. At t equal to t, the value of the inductor current is I naught. So this is our this integral. Now this is the energy stored. So integrating this with respect to I, it will be I square divided by 2, 0 to I naught. Substituting the limits, we'll get the energy stored in the inductor. So the energy stored in the inductor will be 1 by 2 Li naught square. So if the current stored in the inductor is I, then the energy stored in the inductor is 1/2 of Li square. This is very, very important expression. So this much is the energy stored by this inductor after time t, or after the current stored in the inductor is I naught. Okay, this is the inductor and this energy stored in this inductor. All right, let me end this session here.